In this work, we introduce meSch, multi-agent energy-aware scheduling for task persistence. Autonomous robots are widely used for data acquisition tasks such as wildfire monitoring or cave exploration. Most of these missions last for long time horizons, which require robots to recharge. If the robot is not aware of its energy, its battery will die while it's following a nominal plan and will result in a crash. In our previous work, we introduced eWare for energy-aware planning. eWare iteratively generates candidate trajectories which track portion of the nominal trajectory and then attempt to reach the charging station. Candidate trajectories are only committed if the robot has enough energy throughout the trajectory. If not, the robot takes the last committed trajectory back to the charging station. Now consider a scenario where multiple robots share a single charging station. In that case, with only the eWare filter, all robots come back to the charging station at the same time, and thus eWare on its own fails to handle this case. To handle this, we propose meSch. In the meSch, in addition to eWare, we introduce gWare, which ensures that robots maintain the minimum desired gap between their returns to the charging station. Now let's step back and see how gWare works. For n robots, we introduce n-1 gap flags. Here in this case, for 3 robots, we have 2 gap flags. First, we sort robots based on their remaining battery times in an ascending order. Then gap flags are constructed based on the first robot in the sorted list. Since in this case all robots have the same discharge rates, so they have similar remaining battery times. Therefore, let's construct gap flags according to the first robot. The first gap flag is between the first and the second robot, and the second gap flag is between the first and the third robot. Here in this equation, TF2 corresponds to the remaining flight time of the robot 2. TC1 corresponds to the robot 1 candidate trajectory time. TCH corresponds to the charging time, and T delta is the buffer time. Through this gap flag, we want to ensure that if the robot 1 returns using the current candidate trajectory, it has at least TCH plus T delta gap to the second robot. Then we check the second gap flag between the first and the third robot. In this gap flag, TF3 corresponds to the remaining flight time of robot 3, and TC1, same as before, is the candidate trajectory time of robot 1. In this second gap flag, first and third robot are required to have at least twice the TCH plus T delta gap. Since the projected gap is smaller than the minimum desired gap, the candidate trajectory of the first robot in the sorted list is not committed, and it returns, while the candidate trajectories for all other robots in the sorted list are committed. Now let's consider a case when the charging station is mobile. In that case, assuming we know the trajectory of the mobile charging station for some time in future, we construct a candidate trajectory that ends at the projected state of the mobile charging station in future. We also consider a case when the mobile charging station is subject to uncertainty. Now in this case, we use extended Kalman filter to estimate the state of the mobile charging station, and we require a robot to reach the rendezvous point with reserve energy, which allows it to perform a worst-case landing. We evaluate meSch across different case studies and show that it can handle robots with different discharge rates and battery capacities. It is also applicable to general nonlinear robot models and also allows for scalability through distributed implementation. Here we show one of the simulation results where 30 quadrotors persistently follow random trajectories at different altitudes while sharing a single charging station. We also demonstrate meSch through hardware experiments where 2 crazy flies share a mobile charging station while following nominal trajectories.